Hey, Adam, you're live. Start your presentation.
Okay. Okay, so hello everyone. My name is Adam Gonczarek and I'm the Chief of Technology at AlphaMoon. And the title of my talk is 80% of accuracy, yet only 5% of automation. And I'll try to explain you how to implement intelligent automation systems to gain from both. Okay, so here is the agenda of my talk. So I will start with a very brief introduction to the problem. Next, I'll try to answer the question, can we trust AI systems? And then I'll try to show you what are different ways how we can build intelligent human in the loop. And lastly, I will show you a demo of our intelligent automation platform where we are implementing a variant of such an intelligent human in the loop mechanism. Yes, and we will finish with a Q&A session. Okay, so I'll start with a slide that probably all of you are familiar with. So we're going to talk about intelligent automation. So basically, intelligent automation is a just combination of classic RPA systems and artificial intelligence. And in other words, intelligent automation actually extends capabilities of classic RPA with some capabilities of AI, like computer vision, natural language processing, predictive modeling, speech recognition, and so on. And the difference is that classic RPA systems can usually handle only structured data using some fixed rules to process them. And AI systems, on the other hand, can handle unstructured data, can learn from observations, and can generalize over yet unseen new observations. Yes, so just to give you a concrete example of such an intelligent automation system. So let's imagine that we would like to build a system for complaint management. So we have a customer, and a customer is just sending a complaint via email. And you are receiving such an email and passing the complaint into a complaint management system. You are sending back a confirmation of creating a ticket to your customer. And then you are processing such a complaint to your customer service, where humans are reading such a complaint and making a decision how it should be solved. And of course, finally, they are just sending a response to the customer. And this part of the process can be actually very easily automated using RPA tools. So we can basically automatically read emails from our inbox, automatically create tickets in our complaint management system, automatically send a response, and automatically pass the complaints into proper people in the customer service. So the question is how we can extend such a system with some artificial intelligence. So the natural way how we can extend it is use an AI bot which is capable to recognize the reason of the complaint. So the bot is automatically reading the complaints and classifying it into one or more possible classes just to understand what the complaint is about. And you can decide that some of the complaints will be from now processed in a fully automated manner. So it will be solved automatically because they are, for example, repetitive and you are always processing them in the same way. and only some portion of them will be still passed to the customer service. So from now on, you don't need as many resources as you need before, and introducing such a intelligent bot such an intelligent bot helps you with reducing the time and the cost of customer service. Okay, so now I would like to introduce two metrics that will be crucial for the rest of this talk. So probably you're also familiar with those metrics, and those metrics are accuracy and automation. And I think that you intuitively understand that those metrics are somehow related, and that is true. But I will try to convince you and try to show you that there are cases where you can have high accuracy of your AI model. However, the automation will be low. So what do we mean by accuracy here? So accuracy basically is just how precise our AI model is. So in other words, how unlikely our model is to make an error. And in AI, there are many different metrics to measure the accuracy of your model. It actually depends on the task that you are solving. And these are, for example, classification accuracy, AUC, F-score, or, for example, mean average precision, which is the metric that you use, for example, in object detection, mean squared error that you are using for predictive modeling, and many, many others. And on the other hand, automation is how much of human labor we can save when we are introducing our intelligent automation system. And what is important here is that usually our cost reduction is directly proportional to the level of automation that we are achieving. So, of course, when implementing automation in your enterprise for business is crucial to understand what ROI you are achieving. So this is a possible formula how you can calculate your ROI. So this is basically just a product of 4 factors. So we have employees' hourly rate times the time spent for processing a single case by a human employee, times the number of cases that you are processing, for example, daily or weekly or monthly, and times the level of automation that you are achieving in your system. So what is important here is notice that there is no accuracy of your system here. The ROI is basically just proportional to the level of automation. Yeah, so how this all relates to the accuracy? So let's try to answer the question when an AI project will generate value for us. So let's imagine that we would like to solve a particular AI task, and on this axis, let's imagine that we can put every single algorithm that we can create to solve such a task. So on the left side, we will put the most naive, the most baseline algorithm that we can even imagine, so with the worst accuracy. And this, for example, can be like random prediction or something. And on the right side, we will put the highest possible accuracy. This is sometimes called 1 minus base error. Base error is just a theoretical lowest error that can be achieved on a particular task. And probably somewhere close to the highest possible accuracy, we have human level performance. So this is just how humans are, how well humans are solving this particular problem. And maybe somewhere below that, we have the current state of the art. So this is just the best for today, the best algorithm for solving this particular problem. And now let's take the first example. So let's imagine that we would like to create a system for customer targeting for online shopping. So basically, this AI system is just choosing the customers that you are sending offer to and expecting that they will buy some of your products. So if we have a system with, let's say, average accuracy, it is working somehow, it is targeting your customers, and you are already earning some money. Of course, if you have a system with the state-of-the-art accuracy, you are targeting your customers better, you have higher performance, and of course, your profits are higher, your revenue is higher because you are selling more. And now let's take another example. So let's imagine that we would like to create a system for automated invoice payment. So let's assume that you have some subcontractors, you have some suppliers, and all of them are sending you month by month some invoices that you need to pay. And you would like to automate that process. So you would like to create a system that will be receiving all those invoices. Then it will be reading the data and interpreting the data from those invoices. And then it will be creating a transfer to be paid and paying the transfers. And it will be doing it in a fully automated manner. And of course, if you have a method for reading the data and understanding the data that is at the human level performance, or maybe it is even surpassing the human level performance, then you can trust such a system, and probably you can make this work in a fully automated way. However, let's imagine that the current state of the art in reading, for example, data from different types of invoices is high, but still below the human level performance. So in this case, probably you won't trust such a system, and you will expect to do manual verification for all the transfers that you want to pay, because this is so too sensitive process, because there are money, probably big money, that you can believe that you can trust the system that is performing worse than human being. Yes, so now we have to rethink a bit how we should approach such implementation of such an intelligent automation system. So on the one side, we have the situation that we saw in the previous slide. So we want to have accuracy guaranteed, but our AI system doesn't have human level performance. So we need to double check everything. And in this case, because we are double checking everything, we gain from automation only because of collecting the data, maybe reading some of the information from the data, but we still need to go through all the cases and just double check it manually. So the final level of automation that we will achieving will be rather low. On the other hand, we can have a fully autonomous AI system. So this is, for example, the case with customer targeting, where we are achieving immediately full automation. However, our accuracy may be lower than humans' accuracy. So this is, for example, the case in many AI applications at the moment. So for example, we have some applications in computer vision where AI methods already have surpassed the human level performance, but for the rest of them, the performance of such algorithms are still below human experts. This is also the case, for example, in natural language processing, where there was a significant improvement over the last couple of years. However, there is still a gap between what the current NLP systems can do and what is the true human level performance. So we have to think, can we have something in the middle? And I will refer to that something in the middle as intelligent human in the loop system. So what I mean by that, it is a system that will guarantee the accuracy above some threshold. So, for example, human level performance guarantee, human level performance accuracy. However, it will keep the level of automation high. So, to do that, we have to trust such a AI system, at least for some portion of examples that such system is processing, to make them process in a fully automated manner. So let's try to answer this question. So can we trust AI systems? So just to start with a very basic example, let's imagine that we would like to solve a task where we are classifying different types of documents. So in this case, let's imagine that we would like to distinguish between invoices and contracts. So for example, you can just receive those kinds of documents at your email box, and you would like to just recognize whether this is an invoice or this is a contract. And if the document is already classified, you can then pass it to further processing. And of course, this is just a basic classification problem. There are many other classification problems in AI. So you can think of, for example, distinguishing between different types of pictures. This is then image classification. You can think of for example, recognizing the intent of a particular statement or recognizing the sentiment of particular statement. These are all classification problems, and the idea will be exactly the same that I will show you on the next slide. So just to understand how AI systems based on machine learning works, there are basically three notions that you should know. The first one is data. And in this case, the data will be just documents from both of the types. So blue points indicate here invoices, and red points indicate contracts. The other thing that we have to know is an AI model. So in this case, the model is just this moving black line. And for example, you can think of it as a top-notch deep neural network. And the last thing is learning algorithm. So basically, learning algorithm is just a procedure that is feeding the model to the data. And nowadays, all the commonly used models, almost all the commonly used models, so for example, like deep neural networks, have probabilistic interpretation, and you can together with a prediction, you always get a certainty of your model. And basically, the level of certainty is proportional to the distance from the decision boundary. So decision boundary is just the final location of this black line. So in this case, for example, for this point, we can have 99% of certainty that we are classifying this point as an invoice. And on the other hand, if we have a point that lies closer to the decision boundary, the model's certainty can be a bit lower. So, for example, it might be 85%. And you can see that this is actually reasonable because actually in this picture, most of the errors all of the errors actually the model is making is for the points that are lying close to the decision boundary. So close to the decision boundary, your model should be uncertain. So the natural question that probably you would like to raise here is, if we let through all examples with the model certainty equal or above 99%, do we get at most 1% of errors? Because this is, let's say, natural way how we can think of creating such a human in the loop mechanism that will be passing to the human all the examples that your model is uncertain of. And if your model's certainty is above some threshold, so for example, in this case, 99%, you will be processing such examples automatically. But the only thing that you have to take into account is that you can trust your model when the certainty is above the threshold. And unfortunately, the answer to this question is no, and why I will explain you in the next 2 slides. So the problem with AI models is that there are some problematic cases which very often occur in the real case scenarios that will have very high certainty of your model, but in fact your model will be wrong there. So in this case, rather than classifying invoices versus contracts, let's imagine that we are distinguishing between images of pandas and images of gibbons. And we have some cases that we used for training our algorithm. This we will refer as in-distribution examples. And now let's imagine that we are using our AI system and we have some novel examples that actually significantly different from what the model has already seen. So in this case, it could be just a new image of panda, which is different from a new species of panda that is different from the species that you have already seen, or a new species of gibbon, and so on. And for this kind of examples, your model can actually be wrong. Another group will be out of distribution examples. So this can be, for example, image of tiger or horse, or in case of document processing, it will be just a new type of document. So for example, it's some kind of statement or tax office letter or whatever. And the last group is called adversarial examples, and this is actually something that is very characteristic for deep neural networks, that you can slightly change your example that is actually almost the same as the original one, but with those slight change, you can actually fool your AI system. And what I mean by that is, for example, let's imagine that you have an image of a pig and your neural network is predicting that this is a pig with the confidence 91%. And just by adding a special noise with a very, very small coefficient, you are getting the image that visually looks exactly the same as the original one, but now the neural network is predicting that this is airliner with the accuracy, with the confidence 99%. And this is actually the phenomenon that is not only characteristic for images. We have the same problem in, for example, natural language processing. And here we have an example of sentiment analysis problem, where we want to classify a sentiment of such a statement. So connoisseurs of Chinese film will be pleased to discover that Taiyan's meticulous talent has not withered during his enforced hiatus. And here the prediction is positive with the level of certainty 77%. And the first example, you are constructing just by changing one letter in a word connoisseurs into annonceurs. And now the prediction is negative with the certainty 52%. Another example is where you are changing the word film into its synonym, in this case footage, and also the prediction is negative with the confidence 54%. Okay, so we see that we cannot actually trust our model based on the confidence level. So the question is, can we then set a threshold for the model certainty to have statistical guarantees of error less than 1%? And the answer here is yes, but I put a asterisk there because there are two problems with it. So first, you need a lot of training examples to make this estimation correctly. And the other problem is that even if you do it correctly, usually it leads to low automation. So the level that you will choose will be so strict that most of the cases you will be passing for human verification. So the question is, can we do better? Can we somehow extend the way that we are approaching the problem, that we can achieve a higher level of automation? So let's imagine that we would like to create an intelligent human-in-the-loop system. And the idea is that by incorporating a human into the prediction process, our goal is to gain from automation as much as possible while keeping the accuracy high at the same time. So let's imagine that we have an AI problem to solve. In this case, it will be just image classification problem. And we will have an additional method that we will refer to as dispatcher that will be choosing whether we should pass such an example with automated track, or maybe we should pass it for manual verification. And if we pass the example with automated track, then it is processed by an AI model, and the model returns the results. On the other hand, if we pass it through manual track, then it is processed by human, and in this case, human returns the result. And what is worth mentioning here is that it is good to also create a continual learning loop here. So every time a human is manually checking something or correcting something, then these corrections are taken into account to retrain your AI model just to improve its final accuracy. So more technically, such an auxiliary algorithm, so this dispatcher, is actually addressing the following optimization problem. So we would like just to maximize automation, having accuracy above some given threshold. In this case, you can think of a threshold as, for example, a human level performance. Yes, and there are actually there are some possible approaches how you can address this problem, and I would like to mention about two. So the first one is robust uncertainty estimation. So you are just using different techniques to estimate the model certainty correctly. And some of those techniques are called model calibration or Bayesian methods. And the other approach, the other group of approaches that you can use there, we'll call them domain cutout approaches, because these are basically methods that are cutting out the part of a domain where your AI model is performing with a very high accuracy. And we have such a method like out of distribution detection or novelty detection, and many others. One of them I will show you in the next slides. Yeah, so just to show you what is the difference between where you are not using any of those methods, you are just using just a regular AI model to solve your task, and when you are applying, in this case, a Bayesian method for robust uncertainty estimation. So in this plot, on the x-axis, you can see the accuracy threshold that you are expecting. So let's focus on, for example, 99% of accuracy, because this is something close to maybe human level performance. And on the y-axis, you can see the level of automation that you achieve that will be guaranteed here. So where you are using just a baseline AI algorithm, you're achieving something below 20% of automation in this particular example. And if you extend the method with Bayesian uncertainty estimation, you will get something around 50% of automation. And of course, I remind you that the level of automation is proportional to the cost reduction, so proportional to your ROI. So you can see that there is a significant improvement in your ROI when you are using this proper technique for uncertainty estimation. The other method that I would like to show you is something that we are also using. We call it two-model approach. And in this case, we are using another model to model the dispatcher, which is trained jointly with our predictive model. So first, let's focus on the left animation. And we are just fitting the model to our data, achieving 90% of accuracy. And on the right animation, we are fitting two models. So the first one is just our predictive model. This is the black line, and the dispatcher, the other one, is the yellow line. And we see that the dispatcher is actually cutting out half of the plane. And this gives us 93% of automation, but our accuracy right now is 98% because the original model is only operating on the part of the space where it's working correctly. Yes, and here is actually here we have the same results. So this kind of method improves the automation when we have guarantees of an accuracy. Yeah, and at the end, I would like to show you our AlphaMoon Intelligent Automation Platform, which is basically a generic platform for processing any type of documents that you can imagine, because this is just a generic AI tool that can learn from any type of documents and for example, classify them, understand the intent of them, extract some useful information from them. And the idea of the platform is that it's actually capturing data from different resources, from different sources. It can recognize various types of unstructured documents, including PDFs, docs, TIFFs, JPEGs, and so on. And then our AI system is processing those documents and actually converting the unstructured data into structured information. And we are implementing here this intelligent human in the loop mechanism that is actually guaranteeing us that we will have the level of accuracy above a given threshold. This is actually unlikely to what other companies usually offer because very often their human in the loop mechanisms do not have those accuracy guarantees. And once we get results, we can process them further with, for example, RPA systems, or we can make some decision based on them. Yeah, just to show you a couple of applications, we can use it for invoice accounting or CV analysis or credit process management, and for example, for mail automation. And at the end, I would like just to show you a short demo of how such an intelligent automation system works. So I'll play the demo now.
AlphaMoon Intelligent Automation is a platform for document processing. We can process different types of documents like invoices, identity card, insurance policies, or incoming emails, just to name a few. In this example, we would like to process and extract information from uploaded invoice for using Zoom video conferencing service. We can easily examine the details of the extracted fields simply by clicking the field in the main document or selecting an item from the list. Some of the information could not be correctly extracted, and they are marked with the status uncertain, allowing for human verification. We can verify or correct the uncertain fields by using fixed issues. In this case, we have two fields, transaction number and service period. For the transaction number, we can see that the field type and the value are correctly recognized, so we can reinforce the prediction by accepting the results. In the case of the service period, we can observe that the type of the field is incorrectly recognized as sell date. We can easily fix it by changing it to service period and then saving the correction. Once the editing is done, AlphaMoon platform will receive all the corrections and then update the AI model used for processing. This continuous learning and adaptation improves the model over time and reduces the need for human corrections in the future. AlphaMoon Intelligent Automation is a platform
Yeah, and just to conclude, so what I think is worth to take away from the session is that trustworthiness of AI systems is crucial for full automation in different domains. And what I showed you, you can't naively rely on AI models' certainty, because your models can be certain and they can be wrong, in fact. And high accuracy is not enough. To build trustworthy AI systems, you need also robust uncertainty estimation or, for example, domain cutout methods. And intelligent human in the loop can actually effectively manage accuracy automation trade-off. Yeah, so thank you. And I'm not sure how much time do we have for Q&A, but if you have any questions, I'll be happy to answer them now. Yeah, I see that there are no questions. So once again, thank you for your attention and bye.